Swayam Prabha. Digital India. Educated India.
So, last class I have discussed or I have solved different numerical problems to show you how we can determine the velocity and thickness of layers for different cases when we do the seismic refraction test. Layering, horizontal layering case, inclined layering case, continuous change in velocity with depth case. Now, and then I discussed that I mentioned that these seismic refraction test will give you a good result if velocity increases with depth, and why I have also discussed that. Now, there may be in some case in the field that there may be some hidden layer which is very poor or weak, where this velocity will not change with depth or will not increase with depth. That trend will not follow, because most of the cases this trend will follow. But in this, if this trend is not followed, then we will not get proper result. In such case, we have to do this other type of this seismic geophysical exploration. So that is that we can do for seismic cross hole test or seismic downhole or seismic off hole test. What is seismic cross hole test? So in the seismic cross hole test, we have to go for boreholes. So in the previous cases, no boreholes are required. In this, but if that is the case, if we have a hidden layer, then we have to go for boreholes, and then we can easily identify that hidden layer if we go for the borehole. So that means here if we go for the borehole, then we can use one borehole for source and another borehole we can place the receiver. As you can see, this is the source and this is the receiver, and we know the distance between source and the receiver, we know the borehole distance between source and the receiver, and then we can get the, so there will be the direct ray that will travel from source to receiver. So that means we will measure that travel time, and we know the distance, we will get the velocity of that layer, and we can do this test for each layer, because I know where here is, as we are going for the borehole, so it is easy to identify where the layers are changing. So each layer you will get, and you will get the velocity of the wave. Clear? Now another see the seismic downhole and off-hole test. So this is a seismic cross-hole test, two borehole system that can be done for three borehole system also. I mean, we have the source and two boreholes will be used for the receiver. Okay, three borehole system. Now another thing is this seismic downhole test, seismic off-hole test. In seismic downhole test, that one borehole can be used and the source will be at the ground surface and receiver will be at certain depth. Clear? And seismic off-hole test, your receiver will be at the ground surface, the source will be at different depth. That way also you can do this test. But the advantage of downhole test is it is when or the downhole test is most commonly used, as the S wave can be generated easily in case of downhole test as compared to the off-hole test, because S wave, as I mentioned, that is how to generate the S wave, and that will be not easy if it is certain depth. So that if your source is at the ground surface, then you can easily generate the S wave if it is seismic downhole test. Downhole means source is at the ground surface and the receivers are at different depth. Clear? So, depth in the borehole. So, that means in the downhole is commonly used because S wave can be generated easily in case of downhole test as compared to the uphole test. But in the uphole test, your source will be at different depth within the borehole, but receiver will be at the ground surface. However, identification of S wave arrival is difficult at depth greater than 30 to 60 meters. So, that is also another limitation. So, these are the seismic crosshole test, seismic downhole test, seismic uphole test. So, depending upon you have to choose which one is required, because I have discussed seismic reflection test, this seismic refraction test, then seismic reflection test for different conditions, then for seismic crosshole test, seismic downhole test, then you have to use it as per your requirement. So, next one that I will discuss about is the spectral analysis of surface wave or SASW test. So, here the SASW test is performed by placing two vertical receiver on the ground surface. So, that means how it is done. So, if it is this is the ground surface, say, so if this is your source, if this is your source, and I will place two receiver, one is here, one is here. This is my receiver, this is also receiver. Two receivers, vertical receivers on the ground surface, and the distance between the receivers from the source is D1 and D2. Okay, and the del x is D2 minus dy. Okay, so del x is the distance between two receivers, will be d2 minus dy. Okay, now then I will generate the source and then I will generate the wave, and this is the receiver will take these waves. Okay, and the recorded output for both the receiver is transferred to the frequency domain using the first Fourier transform. Okay, so that means from the time domain I have to transfer to the frequency domain by using that first Fourier transform. I will discuss what is first Fourier transform because I have already discussed what is Fourier series. I will also discuss what is first Fourier transform. Okay, so now from there the phase difference can be computed for each frequency, because when you convert to the frequency domain, then I will get the phase difference that can be computed for each frequency. What is phase difference? I have already discussed. Now, the travel time between the two receivers can be calculated for each frequency. The travel time between two receivers can be calculated. Del T is the phi is the phase difference and divided by 2 pi f. How we are getting that? That you know that this is your the travel time is or frequency is equal to 1 by period, time period, that is equal to omega by 2 pi. So, my omega is equal to 2 pi f frequency. Okay. And if we have that a harmonic motion, then we can write this is omega t plus minus phi. Phi is the phase difference and this is A is the amplitude. So these things I have already discussed. So now if we put that ut will be equal to 0, so we can write that that is possible is omega t plus minus phi will be equal to 0. In this case, I can write t is equal to phi by omega. So that is the travel time between two receivers. So t will be phi by omega. Now this is equal to phi, omega is 2 pi f. So that way I am getting the travel time between two receivers. The phi I will for difference phase difference I can calculate for each frequency, and then I can determine the travel time between two receivers, and that I will give you phi by 2 pi f. So phi here is phi f. F means for each frequency. Now the Rayleigh wave, so Rayleigh wave is a surface wave, I have already discussed. So that Rayleigh wave phase velocity and the wavelength can be determined by using these expressions. Okay. Now what is your wavelength? Wavelength is that is equal to velocity by frequency. So that means how I will get the velocity? I know the travel, I know the del x, and I know the travel time difference between the or travel time between the two receivers, or that difference of travel time between the two receivers for each frequency. So that means I will get the del x by del t. So for each frequency I will get the velocity of the Rayleigh wave, because okay, that is surface wave, that Rayleigh wave velocity I will get by using these expressions. So that is basically velocity is equal to x by t. X del x I will get from here, d2 by d1, and xt I will get from this equation. Now your wavelength is for each frequency, it will be velocity by frequency. So this is velocity that I will get from here divided by frequency. Clear? So first I will the recorded output I will convert it to frequency domain using first Fourier transform. Then I will calculate the phase difference for each frequency. Then I will calculate the travel time between two receivers for each frequency. Then I will calculate the Rayleigh wave phase velocity and the wavelength. Okay. Now what I will do, then from there I will get the Rayleigh wave velocity and wavelength. So ultimately I will get the Rayleigh wave velocity and the wavelength. So that is my experimental. If I plot them, Rayleigh wave versus your Rayleigh wave velocity versus wavelength, that will give me the experimental depression curve. So how I will plot that? So I have to plot, this is my phase velocity, and this is the wavelength. So phase velocity I have already calculated, and the wavelength for each wavelength and for each phase velocity I may get this type of plot. Say, I will get this type of one plot. So now next step will be the thickness and the shear wave velocity of the layers are identified by iterative matching of the theoretical depression curve, which is theoretical depression curve, with the experimental depression curve, which is referred as an inversion. So I have to go for the inversion technique. So this is my say experimental dispersion curve. So similarly, I can generate a theoretical dispersion curve also by using the or assuming the thickness and shear wave velocity of the layers. Okay, and then I can use this thickness and shear wave velocity iteratively such that my intention will be to match that experimental depression curve and the theoretical dispersion curve. So experimental dispersion curve and the theoretical dispersion curve, and this technique is called the inversion, and the final value of thickness and shear wave velocity of the layers are identified by adjusting this value until the theoretical and the experimental dispersion curves best fit each other. Okay, this is best fit or fit each other. So that means I have to change those thickness and the velocity of the layers iteratively such that these experimental dispersion curve and the theoretical dispersion curve matches exactly, or there is a base fit each other. Now Rayleigh waves primarily cause the displacement of the ground surface adjacent to a vertical vibration circular footing. Now how I will get the Rayleigh wave? I will generate the Rayleigh wave is of if I vibrate vertically vibrate a circular footing, then the Rayleigh wave primarily cause the displacement of the ground surface as the adjacent to that circular footing. Now SSW can perform quickly, no borehole is required, can detect low velocity layers also, because in the seismic refraction test it cannot detect the low velocity layers. So that's why you have to go for the borehole. But the advantage of the SSW is that it can detect the low velocity layers also and can be used for a depth even greater than 100 meter. Okay, but can be useful for gravel, debris flow deposit and landfill. So this is the advantage of this SSW. So that means in this test what I will get? I will get the again the shear wave velocity and the thickness of the layers by matching the experimental dispersion curve and the theoretical dispersion curve. Okay, and theoretical dispersion curve I will iteratively change or will iteratively change that thickness and the shear wave velocity of the layer. Okay, so now let me discuss that how I will get the first Fourier or what is the first Fourier transform. So quickly I will discuss that because I have mentioned that we will use the first Fourier transform. So let me discuss that part and then I will go back to the next test. So that means here I have already discussed what is Fourier transform. What is Fourier series? So now if I go for the Fourier series, that is Fourier series, you know that we have already discussed that how we can express the Fourier series in terms of trigonometric form. That I have already discussed in trigonometric form. So that means if this is a variable, if this is a xt is a variable, that can be expressed by a0 summation of n equal to 1 to infinity, then an cos omega nt plus bn sin omega nt. These I have already discussed. But still, let me discuss again that where my Fourier coefficient are a0 is 1 by Tf, 0 to Tf, Tf is the period, then xt dt. This is the average basically of this function or variable over the time period from t0 to Tf, t equal to Tf. And an, that is equal to 2 by Tf, 0 to Tf, xt, then cos omega nt dt, and bn is equal to 2 by Tf, 0 to Tf, xt sin omega n dt. From here, how I will get the Fourier amplitude and then the plot between the Fourier amplitude and the frequency omega n is called Fourier amplitude spectra. Okay, so that also I have discussed. So now this Fourier series can be also expressed in exponential form. Can be in exponential form, that I have discussed, that in the harmonic motion also can be expressed in trigonometric form and can be expressed in exponential form also. So exponential form, this variable can be expressed by a0 plus summation of n equal to 1 to the power alpha, then an minus ibn divided by 2 e to the power I omega nt plus an plus ibn divided by 2 e to the power minus I omega nt. So the meaning of all this term omega nt a0, that we have already discussed. Okay, you go to the module 2, and here also by so these, how these equations are coming from here, these cos omega t, sin omega t. So cos omega t is written in exponential form. Those are also being discussed in my previous lecture or module 2. So you see that, and that is expressed in this form. Then you will understand how these equations come. Now here Fourier coefficient are C0 star, that is equal to A0. Why star? Star indicates it is a complex nature of coefficient, because there is a I term, it is a complex nature of coefficient that indicates, that is indicating by star. Now Cn star is equal to An minus Ibn divided by 2, and Cn minus star C minus n star, that is An plus Ibn divided by 2. Okay. So now if I write that variable equal to C0 star now plus n equal to 1 to infinity. Now this will be Cn star e to the power I omega nt plus C minus n star e to the power minus I omega nt. Okay. So now I can write that omega minus n, that is equal to basically minus omega n. Omega minus n, that is basically minus omega n. So in that sense, I can write that this will be finally xt, that is equal to, if I write n equal to minus infinity to plus infinity, then I can write this is simple Cn star into e to the power I omega n t. Now initially it was 1 to plus infinity, now I am getting for minus infinity to plus infinity. So basically these will be simple Cn star e to the power minus omega n t. So the complex Fourier coefficient Cn can be obtained. So now this Cn star, this complex Fourier coefficient can be obtained by using these expression Tf 0 to I Tf xt then e to the power minus I omega n t dt. So Cn I will get from this equation, this is 0 to Tf xt e to the power I omega n t dt. So this is the representation of the Fourier series in terms of trigonometrical form or trigonometric form and the exponential form. Now I will discuss about that what is discrete Fourier transform. Or DFT, discrete Fourier transform. What is that? So now here that x in frequency domain that I will get by using, so initially it was done by integration. Now in place of integration we are doing a summation. So that is del t by summation of k is equal to 1 to n, this is x tk e to the power minus I omega n tk. Okay, you will get that the Fourier coefficient. So this is my Fourier coefficient. So Fourier coefficient is obtained by doing summation. Initially it was this here, this is also Fourier coefficient. This is also Fourier coefficient in complex form, or this is that is complex form. So now that is we are getting by integration. In place of integration we are doing it in summation. Okay. So now if it is doing in summation, this will be xt e to the power minus I omega t into dt. So this will be dt is the small dt. So now it is delta t. So this is the in terms of summation we are getting. Now where your x tk is a variable. Okay, and k is equal to 1 to n. So now tk will be equal to k into del t. If k is equal to 1, it will be del t. If k is equal to 2, it will be 2 del t. Del t is a small time increment. This is the del t. Now I can write that omega n, that will be equal to n into del omega, and then this omega we know this is 2 pi n, and this is time is n del t. Okay, that the total time t. So that is n into del t. Now using the Euler's law, the discrete Fourier transform DFT can be written as, how I can write? So that will be x omega n, that will be equal to del t summation of k equal to 1 to n, and now xt is the variable. Now this I e to the power I omega n t k, that we are writing in cos and sin term by using the Euler's law, that I have discussed in my previous lectures in module 2. So that you will get that xtk into cos omega n tk minus I xtk into sin omega n tk. So that means here the variable is xtk, so that is written in frequency domain. Now if I want to go from frequency domain to time domain again, so that then I have to go for inverse discrete Fourier transform, or IDFT. How I will get? So now I will go to xtk. Initially it was x omega t, omega n, in frequency domain. So now xtk, that will be equal to del omega summation of n equal to 1, summation of small n equal to 1 to n. Then now it will be frequency x omega n into e to the power I omega n tk. Okay, and that you can write in by using Euler's law, that xtk is equal to del w n equal to 1 to n, and x omega n cos omega n tk plus I x omega n into sin omega n tk. So that means for discrete Fourier transform, we will go to the frequency domain, and inverse discrete Fourier transform will go from frequency domain to again the time domain. Okay. So now this the time required for this total process from time domain to frequency domain, and then if you want to come back, then you have to go for the inverse discrete Fourier transform, then from the frequency domain the time domain. So now the time required for the computation is here, time for computation is proportional to n square here. Okay, proportional to n square. Now I will get to the first Fourier transform that we are talking about. Or FFT, first Fourier transform, or inverse first Fourier transform, AIFFT. Okay, so that is, this process is proposed by Coley and Tukey. Tukey is 1956. So what they have done, that you develop computational, so they have developed a computational algorithm where n is a power of 2. That is what is the meaning of that? That increase in size by a function of or factor of 2 to the power n in each stage. So, we will increase the size by a factor. They propose or they developed a computational algorithm where we are increasing the size by a factor of 2 to the power n. So, here in this algorithm, the time required to complete the transform is proportional to n to the power log 2n. So, your DFT, it is proportional to n square, where in FFT it is proportional to n log 2n. So, now let us see, that means it is faster than your FFT is faster than DFT. Okay. So, now let us see that how faster it is. Now, for n is equal to, if I take n equal to 2048, 2048 means your n we are getting equal to this, n is equal to 2 to the power j. Okay. So, it is 2 to the power n. So, it is 2 to the power j if I say, and if your j is equal to 11, then n will be equal to 2048. Okay. So, now here we know that for t, time required for FFT and time required for DFT, these are proportional. So, now that we can write, this is proportional to n log 2n and this is proportional to n square, or I can write this is n log 10n divided by log 10 to the power 2 and this is n square. So, if your n is 2048, I can write 2048, then this is log 10 2048 divided by log 10 2, okay, divided by 2048 square. So, this will be, so if I do that, then the time required for first Fourier transform will be equal to T DFT divided by 186. So, that means the, if your n equal to 2048, then the time taken to complete the transform by first Fourier transform is around 186 times lower than the time required to complete the transform by discrete Fourier transform. I mean, this is 186 times faster than the discrete Fourier transform. Now, similar way we can do that for if j is equal to 10. So, in that case n will be equal to 1024. So, in that case the TFFT is equal to TDFT by 102. That means, if n is equal to 1024, the FFT is around 100 times faster than DFT. And if for j equal to 12, n will be equal to 4096, then T FFT, that will be equal to T DFT divided by 341 times. So that means in that case it is around 340 times faster. That means here this first Fourier transform or inverse Fourier transform, it is the first process, the algorithm that is proposed and which is faster than the discrete Fourier transform DFT. So this is your Fourier transform that I have discussed. So that means here you can see that here, so first the recorded output for both the receiver will be transferred to the frequency domain by using fast Fourier transform. So you will go to the from time domain to frequency domain for fast Fourier transform, then you will get the phase difference for each frequency and then the other steps you have to follow. And now if you come back from frequency domain to time domain again, then you have to go for the inverse Fourier, fast Fourier transform or IFFT. Okay. So this is the end of this today's lecture. In the next class, I will discuss the, so this is also end of the small strain field test. Okay. So I have discussed almost all small strain field test. So major small strain field test. In the next class, I will discuss about the large strain field test. Thank you.